lecture series on theory of equation. Myself, Dr.B.Komala Durga, Assistant Professor in the Department of Mathematics, V.H.N.S.N.C. Virudhunagar. Before going on to the topic, let's look into the introduction of theory of equation. Consider a polynomial with real coefficients, which is a function of the form f of x equal to a naught x power n plus a1 x power n minus 1 plus etc. an, where this a naught, a1, etc. an are constants and n is a non-negative integer and this a naught is not equal to 0. This is a nth degree polynomial and this n is called the degree of the polynomial. Depending on the value of n, we have different name for this polynomial equation. Suppose n equal to 1, then the degree of the polynomial is called, the degree of the polynomial is 1 and the equation is called a linear equation. When n takes the value 2, the polynomial equation, which is of now degree 2, is called a quadratic equation. Similarly, when n is equal to 3, the equation is called cubic, and for n equal to 4, it's a biquadratic equation. The motivation of this lecture series is consider the equation of the form f of x equal to 0. The problem or the objective of our lecture is to investigate the problems of finding the roots of the polynomial, and also we will also see into the relation between the roots of the polynomial equation, and we will also discuss the nature of its roots and the approximate value for the function f of x equal to 0. In today's lecture, we will look into some of the basic definitions and theorem which is involved in the formation of equations. So let's look into the definitions one by one. Here goes the first definition. Let f of x and g of x be two polynomials. We say that g of x divides f of x if we are able to find a polynomial called h of x such that f of x equal to h of x into g of x. So whenever we are able to find a polynomial h of x, then we say that g of x divides f of x. So whenever we want to find out whether a polynomial divides another polynomial, it is enough to find existence of a polynomial like h of x such that this equation gets satisfied. Let's look into another definition. A real or a complex number a is called a root of the polynomial f of x if f of a equal to 0. In other words, we can say this number a satisfies the polynomial f of x. Note that this a is called the root of f of x if and only if x minus a divides f of x. We say that x minus a is a factor of f of x. So whenever a is the root of the function, then we can say x minus a is a factor of the function f of x. Let's look into another definition or the extension of the previous definition. If r is a positive integer such that x minus a power r divides f of x and x minus a power r plus 1 does not divide f of x, then we say that a is a root of multiplicity r. So whenever we want to define a particular root with multiplicity r, then this particular condition must satisfy. Let's look into some of the important theorems without the proof. The first one is called the fundamental theorem of algebra. The statement of the theorem goes like this. Every polynomial of degree n greater than 0 has at least one root. Either it will be real root or it will be an imaginary root. So this is called as the fundamental theorem of algebra. The consequences of this theorem is followed in the next few theorems. So here goes the next theorem, number 2. Every polynomial of degree n greater than 0 has exactly n roots, where the roots are counted according to the multiplicity r. In short, we can say a root of multiplicity r is counted as r number of roots for the polynomial. The consequence of the fundamental of algebra is the next few theorem. For any equation with real coefficient, the complex roots occurs in the conjugate pair. That is, if alpha plus I beta is a root, then alpha minus I beta is also a root. Suppose for example 2 plus I3 or 2 plus 3i is a root, then 2 minus 3i is also a root. Let's look into the next theorem where let f of x be a polynomial with rational coefficients. Let alpha and beta be rational numbers where beta is greater than 0 and beta is not a perfect square. Then suppose say alpha plus square root of beta is a root of the function, then we can also say alpha minus square root of beta is also a root. The condition on beta is that beta is greater than 0 and beta is not a perfect square. So whenever we have a root of the form 2 plus root 3 or 4 plus root 5, then 2 minus root 3 or 2 minus root 5 is also a root. So these two theorems are very important while solving the problem. Let's look into few problems. Look at this question. We need to form the equation with the rational coefficient given one of the root is given as square root of 2 plus square root of 3. So given the root of the equation square root of 2 plus square root of 3, the question is to form the equation, or we need to form the polynomial f of x. So let's see how to find it out. So let's call the root as square root of 2 plus square root of 3 as x. So let x is equal to square root of 2 plus square root of 3. Let me take this root 2 to the other side. So it becomes x minus square root of 2 equal to root 3. Now let me square on both the sides. So when I square it on both the sides, we get x square minus 2 root x plus 2, and this root 3 when I square it out, it becomes 3. On simplification, we get x square minus 1 equal to 2 root x. Let me square on both the sides again to get the final equation. So after squaring it up and simplifying the equation, I get a polynomial of 4th degree x power 4 minus 10x square plus 1 equal to 0. So this is what is a required equation whose root is square root of 2 plus square root of 3. We can actually check whether this root satisfies this equation or not. Definitely it will satisfy the equation. Let's look into another problem. The given problem is solve the equation, and here is a polynomial in 4th degree x power 4 minus 14x cube plus 46x square minus 42x plus 9 equal to 0. Given that 5 minus square root of 22 is a root. So given polynomial is this, and one of the root of the polynomial is given as 5 minus square root of 22. So let's find out the remaining roots of the polynomial. So let me call the polynomial as f of x. And now by the theorem we know that if 5 minus square root of 22 is a root, then 5 plus square root of 22 is also a root. Now let's write down this root in factor form. So it becomes x minus 5 minus square root of 22 and x minus 5 plus square root of 22 are factors of f of x. So we can multiply both of them and this will be a factor of f of x. So we have x minus 5 minus square root of 22. X minus 5 plus square root of 22 is a factor of f of x. On squaring or together we can, this is in the format of a minus b, a plus b. So we can write this as a square minus b square. So which becomes x minus 5 the whole square minus 22 is a factor of f of x. So on simplification we get x square minus 10x plus 3, which is a factor of f of x. We can actually divide this equation, divide the polynomial f of x by x square minus 10x plus 3, we get x square minus 4x plus 3. On factorizing this we get x minus 3 and x minus 1. So let me conclude the problem. The 4 roots of the equation f of x equal to 0 are 5 plus square root of 22, 5 minus square root of 22, and the remaining 2 roots that we got from here, which is 3 and 1, are the 4 roots of the given equation. Thank you. Let's continue in the next series.